Okay, so today we're going to start scientific notation. So in your master digital interactive notebook that starts on slide 50, and you can see from here, we're going to do a definition and there's a little video to watch. So in your math interactive notebook paper, your TOC for today is converting standard form into scientific notation. It's going to be in my notebook, page 10. You notice I drew a line so that I knew that this was the end of the exponents, regular laws of exponents unit. We're going to continue to use exponents in scientific notation. So converting standard form into scientific notation. And again, I'm on page 10 in my notes. So I'm just going to write that on a regular sheet of paper here so that's a little bit clearer for you. There's kind of like dots on that. Take that off. So imagine that you're on page 10 and the top, scientific notation. Now obviously we see the word scientific, see notation, so notes usually are the way to remember something, and scientific, well, may have something to do with the field of science. So what is scientific notation? Well, it is a method of writing or representing very large or very small numbers. Using the power of 10. So some examples that you may use to represent scientific notation could be the distance between the Earth and the sun, right? Or the number of cells in the human body. Because again, remember, mathematicians like to be efficient, lazy, so they want to make things as easy as possible. So what does that look like? Well, we're going to have, name this A, and this is going to be our factor or coefficient. Some people like to call that. It's not officially a coefficient because it's not with a variable, but it is always going to be with a base 10. And there's special rules for this factor or coefficient. We need to have a number, so A must be less than 10, and it can be greater than or equal to 1. So if you think of numbers that fit that parameter, 2, 7.444, 3.12, 9.7, okay? So we can have whole numbers or we could have decimals, but essentially, if you're looking for a number that is greater than 1 or equal to 1 but less than 10, you're looking for a coefficient that only has one digit in front of the decimal. So only one digit in front of the decimal. And it cannot be 0. So the second part, this is where the base 10 comes in, is that this is going to be multiplied by 10 to, we're going to call that the nth power. So here is our exponent. And this represents, we call it base 10. Even though, I mean, if you think about it, it has an exponent, so it's a base, and the number is always going to be 10. Okay. Things to keep in mind that we already talked about this beforehand, but just a reminder that when you multiply by 10, right, your number gets bigger. And if you divide by 10, right, also using a, negative exponent, right, because if you remember, that does the same thing. Your number will get smaller. Okay, so we just kind of need to keep that in mind in terms of how we're going to determine what the exponent is when we change a number into scientific notation. So in other words, scientific notation doesn't change the value of anything. So if I said Johnny has 4 quarters and Susie has $1, right? They both have the same amount of money, but how it's represented is different. Their number of coins is different. So with scientific notation, we're not changing the value of the number. We're just writing it in a different way. So we have to make sure we take that into account when we're performing that duty. So what steps am I going to use to make sure that I put it into scientific notation correctly? So steps to convert a standard number, right, or standard form into scientific notation. So step number 1, I need to make this factor happen, right? So I need to move the decimal so only one digit that is not 0 is in front of the decimal. So that goes to our, A has to be greater than 10, but less than or equal to 1. Okay, so if I have the number 427.3, I would have to move this decimal all the way up in between the 4 and the 2 to make this happen. In other words, this would become 4.273. If I had 0.00052, I would have to move this decimal all the way in between the 5 and the 2, making it 5.22. Now, of course, right now it looks like I changed the value, but remember, this is only the factor. We've only found A. We're going to account for what we added or took away in the exponent that we're going to use, and that's step 2. Count the number of places. We call it places because place value is every digit in a number has a particular place value, a particular order. The decimal had to move in step 1? Okay, this becomes our exponent. Okay, and the sign of the exponent is based on what direction the decimal moved. So if the decimal moved to the right, so like here, we moved the decimal to the right, we're going to wind up with a negative exponent. If the decimal moved to the left, we're going to wind up with a positive exponent, which makes sense because if we look here, I moved to the left and I went from 427.3 to 4.273. So I need to account for taking away, right? Taking away is like a negative. I need to account by that by balancing out with a positive. Here, moving to the right, right? I added value between the two, moving from here to here. So I have to balance that out by taking it away with a negative exponent. So then the third step is combining or writing the number in scientific notation and let's put this up there, up here too. This becomes the factor. Okay, so writing scientific notation by taking the factor that you did in step 1 and multiplying it by 10 to the exponent found in step 2. Okay. So if we go back to these up here, we can see that I had to move from here to here, and that was 2 spots. So I moved 2 spots. Here I moved 1, 2, 3, 4 spots. Okay. Here I moved to the right. Here I moved to the left. So if I took 427.3 in scientific notation, that becomes 4.273 times 10 to the positive second power versus 0.000522 becomes 5.22 times 10 to the negative fourth power. Right? The factor gets bigger, my exponent's going to be negative. The factor gets smaller, my exponent's going to be positive. By the way, this was on slide 53. And this was on slide 50. So slide 50, slide 53 down here in your Math Interactive notebook. And now let's talk briefly about slide 54, which asks you definitions for significant and insignificant digits. And if you remember in rational numbers, we talked about significant and insignificant digits. And we determined that significant digits are a digit or digits that contribute to the accuracy of the number. Right? In other words, we're not estimating. So we want to be precise. So insignificant a digit or digits that does not contribute to the accuracy of the number. So some examples for significant digits. If I have 0.07, right, this 0 is significant. By the way, when we talk about significant and insignificant digits, we're only talking about zeros. Every other number is significant. So you can't get rid of 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, or 9s. So we're talking about zeros, okay? And significant zeros are between two digits that aren't zero, or between or to the right of the decimal, but also have a significant digit afterwards. So 0.007, these zeros are significant. A zero that wouldn't be significant would be 0.7. This, not significant. Significant digit, 10,000. All of these zeros are important. Okay. A digit that wouldn't be important would be 0.1000, where this might be 1/10,000th. But if I was going to write that out, I'd have 1 over 10,000. I wouldn't put these zeros. So these would be insignificant. 407, the zero significant. 0.407, zero still significant. Okay, so keep that in mind when you're writing out your factor, because you cannot drop significant digits, otherwise you will change the value of what you're trying to do. And those are your notes for converting into scientific notation from a standard number.